Okay, we'll have a look at a bilging problem here now where the vessel is going to be bilged at an empty midships side compartment, and subsequently she is going to be heeled. Okay, so we're going to end up having to calculate the angle of heel. Just looking at the formulas here, the formula for angle of heel tan theta is BB1 over GM. BB1 represents the shift of our centre of buoyancy because we're bilged, and GM of course is Km minus Kg. We can't use the hydrostatic particulars, so Km is half the Kb plus the Bm. Bm, because we've been bilged here, it's inertia over our underwater volume. One thing to mention about the volume, the displacement of the vessel doesn't change. Therefore you must, for the volume, use the length, breadth and draft of the vessel. The original draft, of course. Because the displacement doesn't change, you must use the original length, breadth and draft given in the problem. Inertia on the outer edge of the vessel is lb cubed over 3. Obviously it's lb cubed over 12 along the centre line, but our problem is here that we've been bilged here, so we need to find the inertia here on the outer edge and then use the parallel index theorem to get our inertia on the off-centre line. B to B1, there's our original centre of buoyancy there. It's moved there to B1 as a result of our being bilged. So B to B1 is this little area here. So, as always with bilging problems, you must do a sketch. 146, 29.4 breadth, draft 6.52, kg 9.9. The compartment is 24 metres length. Okay. It's got a centre line, waterline bulkhead. So, because of the centre line there, obviously the 29.4, when you're working out the lost buoyancy, you must take that into account because it's only up to the centre line. So as always with these bilging problems, you should always work out the new mean draft. Every time, it doesn't matter where you bilge, let's get the new mean draft, which is the volume of lost buoyancy over the area of intact water plane. Well, the volume of lost buoyancy is the 24 times 14.7, which is half of 29.4, times the 6.52, which is the draft, and there's our volume of lost buoyancy. Area of intact water plane is 146 times 29.4 minus 24 times 14.7. So by doing a sketch, you'll ensure that you don't make a mistake with these measurements. So there's our intact water plane. Sinkage is 0.584. So our new mean draft is at 7.104. Now to calculate the distance of B to B1, we need to get this area here, A times D, and put their final water plane, intact water plane area. This area here we must also multiply by the centre to the centre line to give us the value on top there. So the area times D represents the distance. So A represents the area, 24 by 14.7, and D represents the distance, 7.35. So this is 14.7 here. So from the centre to the centre there is half that, 7.35. So we multiply the, if you like, the lever, the 7.35 by the area, 24 by 14.7, and that gives us the top value. The final area we've already worked out, 39.6. So the distance B to B1, 0.658. So now we've got the first part of the formula point, B to B1, to work out the angle of list. Now let's turn our attention to working out the GM of the vessel. So the moment of inertia of the bilged water plane is lb cubed over 3 minus lb cubed over 3. What that means, it's length times breadth cubed over 3 minus length times breadth cubed over 3. So what we're doing, we're subtracting this small area here from the inertia. Okay, because we've lost that inertia there. LB cubed over 3 minus small lb cubed over 3. So our inertia on the outer edge now has been reduced from this value here to this value here as a result of being bilged. But what we don't want that inertia, we want the inertia about the new centre line. So by the theorem of parallel axis, we're going to deduct from this value here the area times the distance from the outer edge to the new centre of buoyancy. So as you can see here, we're going to say, okay, 1211314 minus the area 3939.6, which is the area of the intact water plane, multiplied by the distance from there to there, which is going to be 14.7 plus b to b1 0.658. We work that out, 0.658. So that's that area, that distance there. We want the total distance, and then that gives us the inertia where we want on our new off-centre line, 282088 meters to the fourth. Bm is the inertia now on the off-centre divided by the volume, and don't forget what I said earlier, the draft doesn't change because the underwater volume hasn't, the displacement hasn't changed, therefore the underwater volume doesn't change. There's our Bm. Kb is half our new draft, that's our Km. We've got our Kg, we're given at 9.9, therefore our Gm is 3.731. Because we've got the Gm now, we can work out the angle of list of 10 degrees. So you just got to remember also on the outer edge it's LB cubed over 3, not LB cubed over 12. LB cubed over 3 minus the area that's been bilged, so our inertia is reduced to this value. Parallel axis takes us back to the new centre line by subtracting from this value the area times d squared, which is the distance from here to here squared. It's the normal parallel axis formula which you've got on your formula sheet. IOZ is IAB minus AD squared. BM uses I over V, which we've worked out there. KB, add the two together, which gives us our KM minus the KG, gives us the GM. Does appear slightly complicated, but I think with these building problems it's just practice. If you just practice 2 or 3 of them, hopefully you'll get the hang of it.